So, hi everybody to the Temporal Graph Learning Reading Group. Today we are very happy to have Emma Ceccherini from University of Bristol. She's a PhD student in computational statistics at the University of Bristol, advised by Ian Gallagher and Dan Lawson. And her research focuses on dynamic network embeddings and generative models for networks. And today she will present unsupervised attributed dynamic network embedding with stability guarantees. And yeah, with that, I'm very happy to hand over to you, Emma.
Thank you. Let me share my screen. Sorry, 1 second. Okay. Do you see my screen all right?
Yes, that's great.
Hi, everyone. I'm Emma. Thank you for giving me the opportunity to present to the Temporal Graph Reading Group. Today, I'm going to talk about our work. The title is Unsupervised Attributed Dynamic Network Embedding with Stability Guarantees. So our goal was to develop an unsupervised method for dynamic attributed graph representation learning that is stable. So I'm going to break down how we define each word in this phrase. So graph representation learning, I'm sure everyone will be familiar with it, is the idea that we have a graph, we have a set of nodes and edges, and for each node, we want to represent each node as a vector in RD, where D is much smaller than N. Then we want this method to be unsupervised. So we are assuming that we do not see the label for the nodes, and we want our representation learning to be task specific. Dynamic, so our graph changes over time, the edges can change over time, and nodes can appear and disappear. Attributed, so for each node, we also have a set of features associated with it, and those features can also change over time. So, for example, if your graph is a social network and your nodes are people, then the attributes could be the age or gender, etc. And then finally, we want this embedding to be stable. So I'm going to explain what I mean by stable. So this is a trivial problem, a trivial simulation for an unattributed graph. So just nodes and edges. So suppose that we have a network and we have two communities within this network. For each node in each community, there is a probability of the node connecting with other nodes in the same community and the probability of connecting with nodes outside of its community. And we have two communities that behave differently. So our stable community or community blue, these two probabilities are exactly the same at time 1 and time 2, while for our moving community, community yellow-orange, these probabilities change from time 1 to time 2. And we would expect the dynamic embedding of these networks to encode both the stable behavior of the stable community and the change in behavior of the dynamic community. Despite the simplicity of this problem, there is almost no dynamic embedding method that can solve it. The first method that was able to solve this kind of problem is UASC, unfolded adjacency spectral embedding. And this was the first method to think in terms of this stability. More, let's say, traditional dynamic embeddings, for example, based on skipgram or GNNs, tend to not have this property. So, for example, you can see that the embedding of community blue from node vec is in two different spots, even though the community didn't change at all. And similarly, for Glowdyne, the community is embedded in two different points. So basically, what we want is the embedding space to have exactly the same interpretation over time. So if two nodes are exchangeable, or by exchangeable we mean that they behave the same within the network over time, that we want them to be embedded in the same spot up to noise. And we want to extend this method, this idea of stability, to dynamic networks with attributes. And we want to redefine stability in terms of both the networks and the attributes or node features. So why would we, care about developing these methods when there are dozens and dozens of temporal dynamic embeddings? So when you want to perform some sort of analysis and graph, as I'm sure all of you know, the state of art is GNNs. For supervised tasks, GNNs achieved very good performances because they get to see the label for each node at all the time points. And so using the labels, the embedding space are sort of aligned, and this leads to a good prediction across time. But when we move to unsupervised tasks, then GNNs sort of break. They're not able to align the embedding space to have a consistent interpretation over time. So when you want to perform dynamic tasks or track changes over time, that leads to poor performances. And that's why we developed AUAC, attributed unfolded adjacency spectral embedding, so that we could have a aligned embedding space that where we could perform any sort of unsupervised task. So we want a point in the embedding space to mean the same thing over time. The core idea of these methods is quite simple, which I believe is an advantage. So we basically assume that the nodes of a graph live on a low-dimensional manifold. As I'm sure you all know, the manifold hypothesis is a very widespread idea, and there are many works that show that this is a fact for large networks, and that it is true that most large networks live on a true low-dimensional manifold, and there wouldn't be any reason to embed a graph if it actually lived in an n-by-n space. And so we try to encode this idea of a manifold hypothesis or a true low-dimensional manifold using a latent position model. So specifically, now that we want to extend the general latent position model to networks and node features or node attributes, we decide to treat each attribute as a special type of node. So we have our low-dimensional manifold where all of the normal nodes, quote unquote, for example, in our social network, where nodes represent people or the people live on this low-dimensional manifold. And then we extend this low-dimensional manifold so that also attributes node live on this manifold. So, for example, if in your social network one of the attributes is age, then we have a node age on this manifold, and the way that the normal nodes people connect to node age is by the edge weight. Is how old they are, corresponds to the value of the attribute. So in order to encode this idea, we have a latent position for each node at each time point in this manifold Z, and then we also have a fixed latent position for each attribute on the manifold I, and Z plus I is our extended manifold. And then the adjacency matrix are distributed according to this function H, conditional on the latent positions. So conditional on the values of the latent position, each element ij of the adjacency matrix is independently drawn from this distribution H. So going, more specifically about H, H is a function of these latent positions Zi and Zj, and it behaves different whether the latent position is the latent position of a true node or the latent position of an attribute nodes. So if both I and J are true nodes, I'm sorry, I have something, let me mute this. So if I and J are both nodes, then H of Zi Zj is equal to 1 minus half of Bernoulli rho f of Zi Zj. So first of all, we have Bernoulli because we are assuming that our adjacency matrix are zeros, one, they're binary. But you could potentially extend it to weighted graphs if that's what you were working with. Then rho is a sparsity parameter, so we are allowing our networks to be sparse. F is some function that generates a probability between Zi and Zj. So in simple case, it could be the distance, but it could be sort of whatever you want. We don't put any assumption on this F. And then you have the 1 minus alpha, where alpha is a weight parameter that I'm going to explain more in detail in a minute. Then what happens if I is a node, but J is an attribute? Then H of Zi Zj is just a distribution of that attribute over the whole network that takes a specific value for that specific node. And then, so that's what F Zj of Zi is. So if Zj corresponds to our node H, then f of Zj is the distribution of H over the whole network. And again, we have our sparsity parameter. And then alpha is a parameter that weights the contribution of edges versus attributes in producing the embedding. So if you have some a priori knowledge that you want your embedding to be you know that your edges are more informative, or you know that your attributes are more informative, you could choose a higher or a lower alpha, but you could also put alpha to 0.5, and then both attributes and edges are equally contributing to the embedding. And then finally, if both I and J are attributes, then we set this function to 0. We don't believe that there could be any meaningful connection between two attributes nodes. Also, I should have said this at the beginning. If you have any question, just interrupt me at any time. Okay, so now we construct this attributed adjacency matrix. So if you think about the idea of having an extended low-dimensional manifold where the normal nodes and the attributes node live, and it all being now everything is a network, then the adjacency matrix looks something like that. So here you have the quote-unquote true adjacency matrix, the nodes and edges between the normal nodes, and then you have CT, which is a n by p matrix, where p is the number of features that you have for each node, and it could be seen as an adjacency matrix between normal nodes and features, and each value of the attribute is the edge weight for that pair. And so since we want the matrix to be symmetric, and we also put it in this bottom corner. And then we have, again, our weight parameter alpha that when you go and compute your embedding, you can choose. And we can construct this attributed adjacency matrix for each time point, because we have dynamic networks. Now we want to embed this big n by p matrix, and we do this using the unfolding. So by unfolding, I mean that we simply stack each attributed adjacency matrix over time next to each other. And so now we create a big n plus p and n plus p times t times matrix. And then we compute the detruncated SVD of this matrix, which is going to be an approximate SVD. And the attributed dynamic embedding, they're simply the eigenvectors scaled by the eigenvalues. So this is a quite simple linear embedding, is sort of PCA adjacent, if you want to think about it in that way, but it's quite powerful. I'm going to show what we mean by that using our estimation theory results. And potentially you could also introduce nonlinearity, and I'll touch upon that later. So before I go and explain our results, we need to add some assumptions. So our first assumption, which goes back to the idea of a manifold hypothesis, is that the expectation of this big matrix is low rank. So that there exists this map phi's that connect from the latent position to the expected value of the adjacency matrix. It's easier for me to think about it in terms of this matrix PC, which is just the expected value of my big unfolded adjacency matrix. This PC is just going to be a matrix of probabilities between each nodes and attributes. And since we're assuming a low rank expectation, this matrix PC has an exact detruncated SVD. So AC is approximately low rank. PC is truly low rank by our assumption. And so we could simply get the embeddings of this PC as, again, the eigenvector scaled by the eigenvalue, exactly the same way as we do for AC. And we call these the noise-free embeddings. That is this YPT. And this YPT is actually the phi of Zi. So the noise-free embedding, the embedding of the expected value of our big adjacency matrix, they have a one-to-one mapping with our low-dimensional latent positions. So that live on this low-dimensional manifold that we're trying to reconstruct. Then we have some other pre-standard assumptions. We want to regulate the growth of the singular values of PC. So we are assuming that there is some level of smoothness in the dynamic of this whole network. We have a fixed number of covariates, so our P does not go to infinity. We assume that the networks are dense enough to recover the latent positions. If they are, we have an assumption on our sparsity parameter rho. If they're way too sparse, we can't meaningfully recover the latent structure. And then we are assuming that the attributes distribution has sub-exponential tail. This is just to prevent very, very extreme values of the attributes, and this is easily satisfied by many standard distributions. Finally, under these assumptions, we're able to prove uniform consistency. So we can prove that the embeddings that are generated from our algorithm, they converge asymptotically to the noise-free embedding YP, which, as I've said before, they are one-to-one mapping of the latent positions in our initial latent position models that live on the manifold. So basically, we are recovering the manifold up to some linear invertible transformation W. So W is just a rotation matrix. And so we can recover the manifold up to some orthogonal rotation. And this convergence is established in the 2 to infinity norm. The 2 to infinity norm is the maximum of the row-wise Euclidean norm. So it allows a much finer control on the elements of a matrix than the standard Frobenius norm, for example. And this, we can show that this norms goes to 0. So the maximum error between our embedding from the noisy adjacency matrix and the true noise-free embeddings goes to 0 as n goes to infinity. And then stability is simply a corollary of uniform consistency. So we say that node time pairs, so node I at time s and node j at time t, are exchangeable if they behave the same within the dynamic networks and in attributes. So the probability with which node I at time s and node j at time t connect to all the other nodes and the distribution of all their features, if they're the same in expectations, then we say that these two node time pairs are exchangeable. So basically, they are indistinguishable one from the other. And we say that a UAC is stable in the sense that if we have two node time pairs that are exchangeable, then they have equal embedding up to noise. So we embed these two nodes that are indistinguishable one from another in the same spot up to noise over time, even if everything around them maybe is changed in two different time points, s and t. One of the main criticism that we get is a computational efficiency. So AUAC is essentially a sparse truncated SVD whose time and space complexity has been extensively studied by people in linear algebra that are much smarter than me. But in our sparsest regime, this is what the theoretical space and time complexity look like. But in practice, our algorithm is pretty simple, and it is indeed very fast. There are very fast packages that allow you to compute sparse truncated SVD. And in one of the examples that I'm going to show in a minute, one of our data set has 500,000 nodes and is observed over 10 years. So our matrix is 500,000 by 500,000 by 10. And to obtain all the embeddings of that matrix, it takes about 30 minutes. So that's, I would say, quite good. Okay, so now onto like some data analysis. Here I'm showing an example using node classification. I would like to reiterate that we are looking for an unsupervised task-specific method. And so our goal is not node classification, but we need to use something to show that our embedding is good and works. And so we picked node classification, but that's not the ultimate goal. The ultimate goal is simply the embedding itself. The idea here is that we do node classification in a dynamic way. So we take our big adjacency matrix, like say observed over 10 years, we embed it all. We train a classifier on year 1 up to 5, the embeddings of year 1 up to 5, and then we test the classifier on the embeddings of year 5 to 10, for example. So the 4 data sets that I have here, DBLP, ACM, and OGBN MAG, they are co-citation data sets. So the nodes are authors, the edges are if two authors worked on a paper together in a certain year, and then the attributes are the words used in their abstracts over that year. And the label is the subject in which they're publishing. While opinions is a customers and products data set. So the nodes and edges are a customer did buy a certain product, and the attributes are the words used in reviews or descriptions of products. And we compared with quite a few unsupervised methods based on some deep learning, some skipgram, various things, and we consistently achieve a higher accuracy. We are the blue line. The orange line is AUAC, the method that I've mentioned at the beginning of this talk, which is where we started from. That is the first stable embedding that is not able, however, to account for node features, especially node features changing over time. And the dashed line is the baseline, which just predicts the most popular class for all of the nodes. And it might be surprising to see that most of DIMS methods are sometimes even under the baseline. And that is because if you train your classifier on a certain embedding, and then at the time point that you're testing, your embedding is misaligned, even if it represents correctly locally your embedding, your classifier is going to be terrible because it has learned on a different embedding space. Finally, I mentioned that we have a parameter alpha that lets you choose how much weight you want to give to the network structure or the feature or attributes, but our results are not sensitive to the value of alpha. So if you set alpha to 0, you're basically not using the attributes at all. So you're going back to UAC, and your accuracy is here. If you set alpha to 1, then you're only using the attributes and you're not using the networks at all. And any values in between, you are doing AUSC. And you can see that, yes, if you choose alpha 0.7, then you're achieving the highest accuracy, but for all the values of alpha different from within 0, 1 are improving on either of the two extremes. Okay. So yeah, another criticism is that linear embeddings using an SVD is not novel, is not flashy enough. And what if I want to use deep learning? I want to have some non-linearity. Well, one at Davis, which was now graduated, but it was part of my research group, was able to show that if the spectral embedding of curly A, with spectral embedding, I mean linear SVD style of embedding, if the one of curly A is a stable, then you can embed this matrix A, you can input this matrix A into a GNN, and the outputs of a GNN are also going to be stable. So this is quite powerful result because it's hard to prove anything about the outputs of a GNN, but it is not easy but doable to prove things using linear algebra. But now you can prove it, let's say on the easier case or doable case, and you can obtain stability for GNNs. And stability is essential for tasks which require exchangeability, like conformal prediction. So here are some references of things that I mentioned in this talk. And this is the QR code of the paper if anyone's interested. Thank you.
Thank you so much. Do we have any questions? Otherwise, I can start with one. You're also very free to put them in the chat. So, I think on one of your slides, you showed this unfolding of the adjacency matrix and then SVD, which kind of made me think of tensor decomposition and like these types of approaches. So how do you know if this research or this approach kind of relates to any of the methods there?
Sorry, I couldn't hear you very well. So you mean sensor decomposition?
Tensor. Oh, sorry.
Tensor decomposition. Yeah. It's very related to that. So the unfolding is one of the way that you could view three-dimensional matrices. So exactly. The one we chose is one, I think 3 or 4 that you can decompose tensors. So the unfolding is exactly that.
Yeah. Okay. Cool. You also mentioned, I'm a bit curious about like scalability. So you mentioned that you ran this on 500,000 nodes times 500,000 nodes times 10 years. Is that like 10 snapshots or?
Yeah.
Okay, cool.
So it's a So I have 10 adjacency matrix that are 500 by 500, and I stuck them all. So now I have 500,000. So now I have a 500,000 by 500,000 by 10 matrix, and I do the SVD of that.
Cool.
And that
sounds
takes
good.
30 minutes. It's quicker than any of the other methods I compared to.
Nice. Any other questions?
I have a question on this experimental setup. So you show some experiments on classification, and I understand that it's somewhat tricky or somewhat impossible to do experiments for the unsupervised setting, but is there any other way to check whether this works?
So we have used link prediction as well in the paper. You could do community detection, you could do change point detection. These methods started for the idea that they were used for anti-corruption, and you wanted to track company reinvention. So someone would come back under a different name, but would have the same behavior of connecting with other companies, and given stability, were able to track that they were the same company. But for the paper, we just used node classification and link prediction because those are just the classical tasks.
Yeah, makes sense. Okay, I see. Thank you.
Can I answer the question?
Of course.
Is this paper accepted somewhere, or it is still under review, or only archive version?
It has been accepted at UAI.
Okay, sounds good. Congratulations.
Thank you.
I have one. First of all, I think this is very inspiring idea to make sure that the embedding of the same vertex is invariant against the time. This is a perspective I personally never have, so it's really appealing, very novel. My first question is about the motivation. It is a very necessary property. We expect the vertex to have same embedding over time, but you said there's a limitation in the paper. Is there any other statements or arguments you can make why such limitation is really important for the graph embedding? And does it relate to the performance, or it hurts some other important theoretical properties? Can you please add more points to this motivation?
I'm not sure I understand your question correctly. Are you asking why do you think stability is important?
I think maybe let's start with my methodology. So usually when I mention limitation in my project, I mean the collaborator will always expect me to make the connection with a very important theoretical property, such as equivariance. Although if practically you want to accept the correlation, that will be how this property hurts the performance. And when I read the motivation session, I think it is intuitively very important that you have the same embedding, that is, this theoretical property is stable, is very appealing. My question is whether there's a close connection with the section you have like the evaluation, empirical evaluation, also your theoretical analysis, how this relates to each other.
So stability is clearly something that you would like intuitively, but it is the only reason why we're achieving such high accuracy, because no matter how much your embedding is able to well represent the behavior in the network locally, if that is not consistent over time, you can't train your model on historical data and test it on the new data, because the new data is going to be completely misaligned with the previous one, and you're not going to be able to learn anything. And as I mentioned before, this started with the idea of doing dynamic tasks, so trying to track if people changed or if their embedding was anomalous at some point. And so you can only do that if your embedding has the same interpretation, if your embedding space has the same interpretation over time. Does that answer your question at all?
Yes, I think it answers my question. Thanks very much. I think when I treat the GNN on the dynamic link prediction in general, I only check the performance. Actually, I'm not really sure in my model there is such a theoretical guarantee for the stability. Also, I will think about it in my research. Another question, my last question is about the evaluation. So don't understand it as a dot, but when I read your table, I mean, I'm not reading your paper now. When I read your paper 2, where you compare the AUC for link prediction and average accuracy for node classification, I have to honestly say this performance is a bit lower than average reported performance. Like for the AUC, you have 0.74, and for node classification accuracy, you have 0.2. Of course, I never run this data set myself. So I would just want to ask whether that the node classification and link prediction problem on this dynamic graph on this benchmark is really so difficult. I remember in general, the AUC for link prediction is already 0.95 plus. And the node classification is also in general higher than 0.9. Yeah, exactly. I'm talking about this table.
But you're talking about opinions, that data set. Because so you could say that 0.3 is a very low accuracy to achieve, but that is because this data has like 20 something classes, and it being products and customers, there's a very high level of noise because people buy a bunch of things. I think we're trying to classifying the category that the person declares as their interest, but you could buy things that are slightly unrelated, or and the attributes used are the words used in the reviews, and so there is a high noise there as well with respect to an authorship network where who you collaborate with and the words you use in your abstract are much more useful to predict your subject than in the other data set. Does that make sense?
Okay, that makes sense. I don't run all the data set, but I run my model on the OGBN, basically your last data set, OGBN MAG. I think when I see the labor board, the best performance now in the world is about 0.85. But of course, if your experiment comparison,
I didn't use the standard version of the data set. So it's, if you could, I didn't explain it here, but in the paper I explained that I basically used only a subset and changed completely the way it's preprocessed to adapt it to solve a dynamic task. So it's not easily comparable to the accuracy given in the benchmark.
Okay, thank you so much. That's all.
Thank you.
I have another question which popped into my mind when we talk about these SVDs and like dynamic network, right? So, and this is maybe a long question, so tell me if you get dropped off at some point. But basically, imagine that we have like a user social network with 100 people, right? And 1 month there's 100 people, the next month there's also 100 people, and then we get these dynamic embeddings each month. That's 100 people, right? Then 1 month, we get 101 users, right? So we've trained on all of the snapshots that have 100 users, and then our new snapshot is 101 user. So in your model, does it
retrain it?
You would need to retrain it, right?
It's there is no in any case, even if next month is 100 user, you still need to do the SVD of the whole thing.
Right, exactly. Yeah, okay. So in that case, like if you're using these embeddings for something downstream, like you're training a different model on those embeddings, then that model would also need to be retrained because the embeddings they're not consistent through retrains, I would assume, right? If that makes sense.
Not necessarily. So the embeddings, because of stability, the embeddings of the networks. So let's say that you embed month 1, 2, 3, and then you train your downstream model, and then month 4 data arise, and you need now to retrain to like re-embed month 1 to month 4.
Yes.
The embedding of month 1 to month 3, they're going to be exactly the same as the one you did before up to orthogonal rotation. So you're going to have your downstream model to be up to orthogonal, like to be able to detect, to allow for the orthogonal rotation, but up to that, they will be the same. So you wouldn't need to retrain your downstream model necessarily.
Okay. Up to, like, assuming that it is like orthogonal, that it kind of accounts for that, right?
Yes. If it does not account for that, then you might have everything rotated. But they all of them are rotated consistently, but they have one rotation with respect to the true manifold. So if the second time you do it, it's because of there is not one canonical choice of SVD, basically.
Yeah, exactly. Yeah.
If you're able to prevent that. Sorry.
But if you're training something cheap, then that's no worries. Then you just retrain the whole shebang, right? But yeah, okay. I was just thinking, SVD, and if you need to retrain everything, but that's cool. Thank you.
Thank you.
Have you now? I'm just firing questions because everyone can chip in the comments. Have you tried, like, what if you push this to the max? Like, how big will it go? You said the 500,000 nodes times 500,000 times 10, right? Can we double that? Can we triple that? Like, what if we have daily granularity and we have 365 snapshots or something like that?
So I've never in practice tried anything larger than that. I presume you could double that, like, without many issues. I think you would run into memory issues earlier that you run into it takes too long to compute the SVD issues.
Okay.
But if you want finer granularity, the work we worked on before this, we extended the same idea of stability, but for continuous time. So you're now, instead of getting an embedding, you're getting a continuous curve of the trajectory of the point over time. So that works the finest granularity that you want.
Cool. Thanks.
Thank you.
All right. I think unless there are any other questions in the comments, then on behalf of the Temporal Reading Group, Emma, we would like to thank you so much for spending your afternoon here with us and talking about your paper. It was super cool, and thanks everyone.
Thank you so much for having me. Thank you. Bye.
Bye.
Thank you. Bye.